Well, hello everybody, and welcome to the second lesson of the language model introductory course. Today we are going to look into neural approaches to language modeling. One actually, quite a fundamental one in my opinion, and then we have a look at word embeddings. And a brief recap from last time. We had a look into what language models are and the n-gram language modeling, which was the statistical approach to language modeling. We saw what context means, probability calculation, calculate the probability of a word given a context, what it means generalizing, and zero. So what happens when we calculate the probability and of a chain of a sequence of words and we get a zero. So what happens within the n-gram approach. We also saw the relationship between a corpus and the modeling and the influence that the size of the history has with respect to generalizing, generating probabilities and calculating probabilities and generating text. The good news is that we have recordings, so you can go back and have a look at the previous lesson, and now we also have a GitLab repository, so you can go and get all the material. I'll try to upload. This lesson is already in the repository, and next week we talk about recurrent neural network approaches to language modeling. So I'll make sure, like this time, that the material for next week's lesson is present in the repository before we go through during the lesson, so you can familiarize with it already by yourself. Now, given that you're all experts in machine learning, given the self-reports, I did prepare this introduction about artificial neural networks. I'll go through it extremely quickly, so hopefully we spend more time chatting and discussing about the neural approaches to language modeling. So, artificial neural networks can be seen as a function that maps an input x to an output y, usually represented as a vector. So it can be multiple features in input and multiple features in output. And a neural network is this function inside here. The historical the origin of artificial neural networks were more rooted into neuroscience with the McCulloch-Pitt perceptron and neuron. But nowadays things have been drifted away, at least in my opinion. We are not really, sometimes we read that neural networks are, simulating the brain or human brain, these sort of things, but to me, they are not really doing that. There are different neural network approaches that do that, but for language modeling, we don't really do that, in my opinion. A core component of artificial neural networks is the perceptron, which takes an input, again, a certain amount of signals, in this case, this vector x with n features, and produces one output. And the perceptron generally is composed of two functions, function g and a function h. H is called the activation function. G is in charge of, in a way, compressing the vector in input into one single value. Usually there is an additional feature to G, which is called the bias, which has value 1. And the combination of these comes through a weighted sum of these inputs. So you can see here the formula of G, and then we have the activation function H, which can be introducing non-linearity, non-linear relationship, let's say, between the input and the output. The input to H is an example of activation function, like the sigmoid function, which was very popular back in the days. That converts, the sigmoid specifically converts an input that can go from -infinite to +infinite to the range 0, 1. Other examples are the arctangent that maps values from -infinite to +infinite to +-1. and then the rectified linear unit activation function, which arguably is one of the key contributors to the explosion of deep learning, or at least the advent of deep learning in the last years. I made an example of Perceptron, which is the OR logical operator. As you know, it takes an input two values, A and B. You can see it here in a column form, and this is the output that you will get. And the idea is to train a perceptron to output, to predict these values, 0, 1, 1, 1, given these different inputs. This is an example. We can set the values randomly, and then we can get the results. This is the true value. So in this case, we talk about supervised learning in the sense that we want to adjust the weights of our perceptron so that the output that we calculate, our prediction, align with the ground truth, with the labels, with the values that we provide for supervised learning. Then we can calculate an error to see how much we are away from the ground truth. And this is the values. And this is the total error. The total error is calculated as the sum of the square errors. We can play with the values as we want, but we're all experts, so I'll continue. But we can do. Actually, I'll give you the solution. Maybe not. Actually, we can play with it a bit. We have time, so we can think about. Okay, let's set W0 to 1. You see that the error decreases. Now we can think of let's add another one. Let's set it to 1 again, because if you think about it, if we sum these two values if we multiply these values by these weights, and then we sum the bias with this weight, we get closer to the OR function probably. As you can see here, I think the error increased. We can play with it. We can add a 0 weight for the bias, so we basically ignore the bias. Pay attention to the error. See the error decreased a bit. I forgot that there is the activation function, which is the sigmoid in this case, and then we can play with it. Once you play with the code, you can set your values and find the solution, which I know, but I'm not going to tell you. Let's continue. On a graphical perspective, the neural network, or the perceptron in that case, identifies a decision boundary, or allows the definition of a decision boundary according to which the inputs can be then classified into 0, 1, which is the same as the OR classifier, the OR logical operator, sorry. We have a neural network that classifies, and we have a logical operator that we try to approximate to. And with a single perceptron, we can identify this decision boundary for simple logical operations, such as OR, AND, NOT, and so on. Problems arise when we deal with more complicated functions, such as the exclusive OR. And this was actually a huge problem in the history, in the research in neural networks, because there's no such a thing as one decision boundary that perfectly splits the input so that the output match. And you can see it in here. We can use the OR perceptron, and we can see that we always introduce an error. It's not possible with one such line to have a perfect classification. So through research, an idea emerged, which was to increase the number of perceptrons and link them together. And this led to the definition of a so-called multi-layer perceptron. And nowadays it's just called artificial neural network. And nowadays the term deep learning comes from having many of these layers of perceptrons. We have an input layer, which is the one that processes the input, the output layer, which generates the outputs, and everything in between is called the hidden layer. And you can see that the calculation is still a function, and it becomes a nested function of all these intermediate layers and their activation functions. Nowadays, we have libraries such as PyTorch and TensorFlow that allows us to define these networks and getting, let's say, being more focused on making complicated networks rather than implementing them, if you want to say it in that way. There is, of course, a solution to the exclusive OR, because nowadays we can achieve so many things with artificial neural networks of deep learning. The question is, when we have a big network and we have so many weights or parameters, if you want, that we need to fine tune, like we did for the OR example, the question is, how do we find them? How do we find these parameters so that we get a perfect classification, perfect prediction, or at least a prediction that gives us the minimum error? And a way to see that is the following. You can imagine that we have a parameter space, which is the possible combination of all parameters of our network, and a loss, which is what we calculate to what we use to calculate how far our predictions are with respect to the ground truth. And the example of the perceptron that I showed you before, we relied on this formula, which is the residual square errors. And the idea is that, imagine you have some weights, we calculate our predictions, we calculate the loss, and we get a certain point in the loss curve. What we want to do is analyzing this curve. If we are able to analyze this curve, we can see that by adjusting the parameters in a certain way, we can reduce the error. And by doing that, we can make little incremental advancements in these parameters so that the error loss of the loss is reduced. And then we can do that in an iterative way so that we eventually reach a local optimum. I think there was a mistake in the setting of the slides, but you get the idea. By making incremental changes to the parameter space based on where we are in the loss, and based on where we are in the loss, that essentially means that we can analyze the derivative of this loss function and follow the negative direction or the negative sign of the loss. We can reach a local optimum. Why local optima? Because if we keep going greedily, if you want to say it in that way, along the negative slope of the derivative of the error function, once we get to this local minimum, we reach a local optimum. We don't know if it is the global optimum because we don't know the full landscape, at least given our observation here, or at least given this position that we are with respect to the parameter space. What I described you is essentially what gradient descent does. Gradient descent is another fundamental algorithm of artificial neural network and deep learning. To give an example, I prepared this data set of random values that range from 1 and 10, and y that is a linear function essentially with a true weight that is of this value, 0.2, randomly generated. And the idea is to train a perceptron to align, to predict these weights. This is the formula that the perceptron will calculate. So you can see the weights multiplied by the inputs. This here is our loss function that is defined in programming language in this way. And again, there's, I don't know why, but the fraction symbol line is not being shown, but this is how we calculate the derivative of the loss function with respect to the weights, so that we can move along the parameter space axis. And this is the derivative of the function that you saw before, the residual square error. The update that we do, so those incremental steps that I explained before, are the following. We have the current weight. We calculate the derivative of the loss function with respect to the weights, our parameter space. And we subtract to the weight this derivative scaled down by a parameter alpha, which is the learning rate. So alpha regulates how much we move from the current parameter space configuration. This is the example that we set up. So we start from an initial weight for our neural network or perceptron which is this value. So we start from minus 1.45 and so on. And we want to adjust the weights of our network so that we reach 1.76. We can do that with a certain amount of iterations. In this case, we have 10 iterations. And you can see, maybe I should go up a second. Here is the equation that where we adjust the weights. And what we obtain in the end is this. Is the following. So we start at iteration 0. We have these predictions, these red predictions that are very wrong with respect to the true predictions. This was our loss, initial loss, and this is the value of the weight that we had in our network. And through gradient descent, we basically adjusted the weight, we reduced the weight, we reduced the loss, and you can see here in the trend that slowly we align to the true values. There's nothing wrong with the plotting, but you can see that the loss gets to 0. Say 0.0055. Or it can even be adjusted more. Well, the difference in the y-axis is relatively small. We mentioned the exclusive OR example. I'm not going through it because, again, maybe you're spending too much time on it. But there is the code in that you can reach, and you can have a look at it. You can run it multiple times. You can see here. In this example, you can see that this is the loss of this neural network. In this case, it's a multi-layer perceptron. So there is an input layer, hidden layer, and output layer. The hidden layer contains 2 neurons, or 2 perceptrons, if you want. It has a sigmoid activation function, if I'm not mistaken. This is a loss. This code is written in PyTorch. Highly recommended to familiarize with and to play with. And this plot shows the accuracy, so the prediction, so what the network predicts with respect to the inputs that you get. And you can see that we achieve perfect prediction. So 1 accuracy 1. So we have 4 inputs and we get four correct predictions. And this is the loss that you can see it gets close to 0. We could have introduced some stopping criteria, not to let it run so much, but this is what the code is. This is another example. Some weights, you can even put them on a spreadsheet and play with it. What I find interesting is that there is a moment, this was run a few days ago. This is the same plot that you saw before with the loss and the accuracy. And you can see there is a certain point in which the loss is quite constant. Nonetheless, the accuracy changes. So there are still some weight adjustments that don't improve neither the loss, but they still flicker in the accuracy. So you can interpret it as the network trying to figure out what's going on, if you want, again, to anthropomorphize this simulator of the brain, if you want. Now, let's move on from generic neural networks and talk again about language models. And let's talk about a neural probabilistic language model. The idea of neural language models is to use neural networks to predict the next word given previous words. So we're still within the same domain that we had with n-groups. Representing the next word in terms of neural networks can be achieved by having a number of output neurons, which is the same as the size of the vocabulary. So you remember we have a corpus, we can extract the vocabulary. Maybe we can put some unknown words if we want, and the same of what we did for n-grams. And then we can map the output of this vocabulary to the output of a neural network. What we want to do is to predict or calculate probabilities. So recall that we have 1 neuron per vocabulary item or word in the vocabulary. And this neuron, the output neurons with activation function eventually can return a probability or a value between 0 and 1, logits, if we can use that term. The idea is that we need to convert these logits, which can be interpreted as the probability of a word given context, but evaluated independently of each other. So we want to convert this into a probability distribution, which means that the integral or the sum of all probabilities equals to 1. And we can do that by a very common function called the softmax, which is defined as follows, which then squeezes basically these probabilities into a probability distribution. What remains to define is representing the previous words, because neural networks accept input numbers, but we have words. So the question is, how do we transform words into numbers? Recall that n-gram models represent words as unique items, and it's a node in a graph, and or a key in a dictionary with respect to the previous class. So how do we do that with neural networks? What Benjo came up with is an approach. This is the paper that defined this a neural probabilistic language model, which to me is a brilliant paper. And I guess I haven't found a paper written by Benjo that it's not brilliant. What he proposes is a way to learn these values that define, these numbers that define words, and the joint probabilities function of all words together, the context, in order to predict a word. Sounds a bit weird. I'll try to repeat it. So I'll use his words. His approach is based on 3 steps. The first is to associate each word in the vocabulary with what he calls a word feature vector. So a vector, each word has a vector of values. The second is to express the joint probability function. Joint means that we have a context of a sequence of words, so that's the joint. Remember from the previous class when we had the introduction of probabilities, the joint probability is the product of all these words, the probabilities of these words. So the joint probability of these feature vectors. And the last step, which is the fundamental, or one of the fundamental ones anyway, it's learn simultaneously the word feature vectors and that probability function. This is achieved by a simple feed-forward neural network. It has some possibilities to skip the intermediate step. I won't go into it, but the idea is that these feature vectors, word feature vectors, are stored into a table lookup. So you can imagine a table that has as many rows as the vocabulary and as many columns as the dimensionality of these vectors. And every time we take an input, a context, so a certain amount of words, in this case 3 words. So this paper focused on 3 grams, compare their approach to 3 grams. So we go and look at the 3 indices in this table lookup. The vectors are extracted, and then there's the second step, which corresponded to the joint probability function, which is essentially the neural network, the hidden layer that concatenates these vectors, and then through a nonlinear activation function, which is the arc tangent in this case, then it leads to a final output layer with softmax activation that returns the probability distribution of the next word given the context. And because this is a unique neural network, we can introduce a loss, in a prediction loss, and then backpropagate it through gradient descent and backpropagate the error. So adjust all these weights, and as a consequence, we can also adjust the values in this lookup table. So we can adjust the word feature vectors. There is an interesting, again, this paper was written in 2000 and feels quite old if you think about how we advanced in deep learning and so on. But there was this interesting sentence in the paper that says that the feature vectors, so at this point, the beginning of the processing, if you want, the feature vectors associated with each word are learned because we put them in the pipeline with gradient descent, but it can be initialized using prior knowledge. And in this case, prior knowledge might mean adjust the weights as initialization and then let the whole gradient descent algorithm work. But nowadays, what we do is we can retrieve these feature vectors, from repositories. Try not to use some terms that we use later, but essentially these are word embeddings that we can download, plug them in, and then train the subsequent bits of the network. And in this case, we talk about the downstream task. Now, let's get to the recipes again. This time we use 10,000 recipes. This is the size of the vocabulary, 5,300 words in 10,000 recipes. It's quite a rich vocabulary if you think about it. This is an example of a recipe that is in our training corpus, and what is being fed to the neural net, to the probabilistic neural network, language model network, is the indices to the lookup table to retrieve the vectors, and then the index of the word to be predicted. So in this example, we had the first recipe. And so if we look at this, we take the first 3 words in heavy, which is here, which corresponds to the 0th, the first and the second vectors in the lookup table. And what needs to be predicted is num, which corresponds to the 4th word, or the third in this case, because we start from 0th, or let's say the word at index 3 in our vocabulary. These were the hyperparameters that I set up. So the feature vector lookup table has 5,300 words, 5,300 rows, and 20 columns. So each word is represented by a vector of 20 values. And these are some other settings that you can play with. This is the learning rate, and this is the number of epochs, so the number of iterations of this gradient descent algorithm. And it's relatively small, and that's because you will find out more in the subsequent lessons. But you can adjust it the way you want. You can increase it and see what happens. This is the result. You can see that out of these 5 epochs, the loss decreases, the accuracy in prediction increases. We're not going to go through the details too much, because what I want to focus on is on the generation bit, just to have a comparison with the n-grams, and then the feature vectors. So if you want to generate text, one thing we can do, you remember from the n-gram lesson that the idea is to take this probability distribution and then sample a random number, and then obtain the word corresponding to the probability value, and then output the result. In case of neural language models, one additional, but it can be done also for n-grams, but one thing that is very common for neural language models is the introduction of 2 parameters with respect to text generation. One is temperature, and one is top K. Temperature is a parameter, in this case tau in this equation, that aims to squeeze the probability values towards uniform distribution. So the lower the temperature, the higher the temperature, the more towards the uniform distribution. When temperature is 1, we had basically the same output that we get from the neural network. And then top K, or sometimes you also see top P, it's a way to trim this probability distribution and rely on the top K, or the highest K words with the highest probability, or the top P, so we can limit or extract as many words or candidate words that have a predicted probability higher than a certain threshold. By using these 2 parameters, we can adjust how random the generation of text is. And I'll give you an example here. This is based on the training on the model, the neural probabilistic language model that you find in the notebook that was being trained on those 5 epochs. And given an input of a sentence that was add onions and, I think, but you can look into the code. The network outputs this probability distribution. You can see it's fairly flat, except for a few spikes. And you can pay attention to the y-axis scale, that if we increase the probability, basically we divide the logits and therefore the probabilities by the probability. And you can see that the more we increase the temperature, the lower the maximum probability. So they all get squeezed towards zero, so towards uniform distribution, because they all tend to have very, very similar values. Then we can do selection. We can use top K and take the K highest, the K words with the highest probability. In this case, we have 10 words. This is the magnification of it. These are the 10 words with the highest probability. And what we can do again is convert that into a probability distribution and then sample the same way we did for the n-grams. You can see that independently on temperature, the top K words are always the same. But of course, we can select the words and then increase the temperature so that we get towards a uniform distribution of the top K words. Let's try to generate text. So this is the temperature value. This is the top K. This is the input that we give to the network. So what happens in this loop is that these words are being indexed. We retrieve the indices of these words in the lookup table, and then we ask the model to predict the next word, and we do that by applying the temperature, then selecting the top K words or logits. Then we calculate the probability, so we retrieve the probability distribution, and then we sample. Then we extract a word, we append it to the sentence, then we take the last 3 words, and we continue iterating until a stopping criteria is being met. And in this case is until the sentence has as many words as we want. Or I think we can even add the constraint that the moment that the network generates the stop sentence word, that we stop. So it's running, but it's not running. There's an error. Let me go back and have a look. I'll rerun it, so then I'll show you what's going on. Let me just train again. See here the 5 epochs. And wait a bit, or I can continue. We can get back later, but it's generally quick, I think. In the meantime that we wait, are there any questions? Everything is clear. Okay, well, I'll tell you what, I'll continue, and then we can have a look at how words are being generated. Because what I would like to talk to, and we are transitioning to the next topic, is the feature vector. So let's have a look into it. And yes, this is an example of a generated recipe from that newly trained network. And add onions and was what is being given. Then you can say generates pepper, which is, if I'm not mistaken, was the same, the most common word also for n-grams. And then it continues, and you can see again that the sense that the recipe that has been generated doesn't really make too much sense. Remove from heat. Yeah, well, there's bake, so there is heat, so there is something going on there. But you can see here that bake at stops. I suppose it's because we achieved the number of words, 20 words. So we truncated the generation. But
Corrado, may I ask you a question?
Yes.
How many words are used as inputs for each step?
3.
So every time 3. So when you predicted cover, you were using onions and pepper, right?
Well, it's and pepper and new line, which is a token that was introduced to tell the network to generate the next instruction. But yes, that's the idea.
Okay. Okay.
So to generate, to get we fed cover and bake to the network, and the network predicted at. and we gave and bake at, and we got num, and so on. It's a bit like n-grams. It's very similar.
Another question would be, how does the temperature influences the prediction of the text generation? Can we see?
Let's try. Oh yeah. Let's set temperature to 10, and you can see here that doesn't really make much sense. We can even increase top K if you want to get even more possibilities to sample words, and you can have an idea. To me, this makes less sense than when temperature is low. Because if we go towards uniform distribution, it means that all words are equally likely to be chosen as next word. Does it make sense?
Yes, it does. But then when would you choose for a higher temperature than 1?
Well, maybe 10 is a bit too much, but when you want to have a bit more creativity in the generation of text. Now, in this case, we talk about a fairly simple model that was being trained over 5 epochs only, but you can imagine that if we train this model on a much larger corpus of, I don't know, 1 million recipes, and for thousands of epochs, then the network would have been very able to generate coherent recipes, if you want. So by increasing the temperature, we would give the chance to the sampling of to deviate slightly from greedy sampling.
Yeah.
And then still generate coherent recipes, but still with some variability in there.
Oh, I understand. Perfect. Thank you very much.
Sure. Okay, so we said about the feature vector. Let me try to Yes. Okay, this is taken from the Żurawski-Martin book. At the end, you will get the references of all the chapters and that they were used to create this lesson. There's this interesting sentence that says that it makes sense, and I'm by far an expert in natural language understanding or processing, but it makes sense that words that occur in similar contexts tend to have similar meanings. It's a bit like oculist and eye doctor. They are synonyms, I would say. So they would occur in the same context, so with the same words being around them. And if we talk about having feature vectors that represent words, the term similarity can be represented by different metrics. So we talk about vector similarity. And a very common one used in NLP is the cosine similarity, which is defined as the dot product. It takes an input 2 vectors, and the cosine similarity is the angle between these 2 vectors. And it's defined as the dot product of the 2 vectors divided by their length. And when the angle is close to 0, then the cosine is close to 1. And then we talk about very similar vectors. On the other case, when the angle is close to 19, then we talk about orthogonal vectors. And then we have opposite vectors when the angle is 180 and cosine is -1. So cosine similarity ranges between -1 and 1. We can have a look at the feature vectors and the cosine similarities of the trained neural network that I showed you earlier. So in this piece of code, we want to see we want to extract k vectors or k words which have some relationship with onions. By relationships, I mean in terms of cosine similarities. So it was pre-calculated. I think because we retrain, we need to recalculate the similarities, but you can do it. But since this was done on a previously trained network, you get the idea of it. So in this case, we want to obtain the vectors which cosine similarity with respect to onions is closer to 0, and we get these values. So again, cosine is 1 when the angle is 0. So you can see that onions is very similar with respect to the context, with carrots, celery, mushrooms, vegetables, and onion. like there's onion and onions that are very similar to each other. It's a bit surprising that carrots are more similar to onions than onion. But again, consider that we trained the network only for 5 epochs. We can go and look at the orthogonal words to onion, which are these weird words that are present in the training corpus. Or we can try other words. So we can go and look at the most similar words to fry, and you can see that we obtain verbs related to cooking. So cook, defrost, there's huge, there's semi. So if we want to stop at the 2 highest, k equal 2, we would get these two words or 2 verbs. And then we can go and look at the orthogonal words to fry, and we get these words. You can see that their cosine is 0, so they're perfectly orthogonal. Again, keep in mind that the network was trained for 5 epochs only. So I would say that if you train for longer epochs, you will get clearly different results. We talked about that, about the feature vector. Well, through time, the term feature vector evolved. I don't know if you're all familiar with deep learning, so you know that the feature vector is a core component of convolutional neural networks. So your deep neural network is, also about end-to-end learning. So the features are being learned. So we don't do standard machine learning with feature extraction, feature selection. And this is what we did with this language modeling approach. So we have this feature vector that converts words into values, into numbers, and then we train the network. And this whole idea to convert words into numbers is a core aspect of NLP nowadays, modern NLP. And again, taken from Joravsky Martin, the idea of vector semantics. But by semantics, I don't know, to me, maybe semantics is a bit of a debatable term, because semantics is the meaning of a word. Instead, we just convert a word into a vector, but never mind that. We can discuss that if you want later on. But the idea of vector semantics is to represent a word in a multidimensional space that is derived from the distribution of word neighbors. So given the context, we can represent the word in a vector so that similar words are close to each other. This is a representation of the vectors of the neural network that we trained before. Remember that the feature vector of the network that we trained before has dimensionality of 20, so 20 values to represent one word. And this type of visualization is achieved by an algorithm called TSNE. It's a sort of dimensionality reduction that squeeze these 20 feature vectors into a 2-dimensional vectors. The idea is that through that, it is possible to visualize these high-dimensional vectors, and it is possible to show similar words. In this case, I can read celery, garlic, they're very close to onion, and the orthogonal vectors, which were drop, containing. This comes from previous training. You can see they are further away, even in a 2-dimensional space with respect to onions. Maybe let me have a look if there's something else in here. Yes. Well, the idea of finding these word embeddings, as I said, is fundamental in NLP. And if you think about it, what was done in this very network, this work of Benjo, was to train or to learn this word representation, this word embeddings from the training corpus. The idea was to predict the next word, but through that task of predicting the next word given a context, we learned these word embeddings. And this approach of guiding the network to learn these representations given a corpus or without labels, because we didn't know the true values of these word embeddings, is part of this very important machine learning paradigm called self-supervised learning. And we also had a course on self-supervised learning a while ago. Maybe Alireza can explain later, maybe not. But it's a fundamental technique, paradigm that is also being used nowadays when we have this huge amount of data and investing time in manually labeling data points is too costly. So the idea of finding, if you want, creative ways to self-supervised learning, to learn semantic representation of words, is of paramount importance in NLP. And this whole task of self-supervised learning belongs to this whole realm of representation learning. So learning a way to represent data in a space, in a latent space that can be used by neural networks in our case, or by deep learning approaches. There is one interesting aspect of word embeddings with respect to similarities and their semantics, and that's the fact that if these embeddings are representing words very well, then it is possible to perform arithmetics in this vectorial space, and that to some extent translates into the semantic operations on words. This is an example of word embeddings obtained by an algorithm called, or approach called GLOVE, comes from Google, that shows that there is some sort of geometrical relationship between words. You can see in here we have adjectives, and I forgot what is it called, but they're slow, slower, and slowest, that has this sort of path or trend or connection in this two-dimensional space, and the same with short, shorter, and shortest, and so on. So it's the same. I guess it's very common to see that men can also perform mathematical operations, as in man is to sir as woman is to, and by looking into the vectorial space and the word embedding space, we can obtain ma'am. The word embedding research, in my opinion, really exploded in 2013 with the work of Mikolov and colleagues, specifically with the definition of a model called word2vec that focused on learning word embeddings given a corpus in a self-supervised manner. The focus of these two works, the second one is basically an improvement of an approach defined in the first work, was to create basically a language model, so to predict a word given a context. But the focus of the whole work was not on predicting the next word, so to create a language model, but just on creating these embeddings. So that's also this aspect of self-supervised learning. So we have this ground truth that comes from these sequences and the relation that words have with each other, but the focus is on creating or retrieving a representation of these words in a vectorial space. And word2vec generates static embeddings, which is something that we will address next lesson. But what that means is that given a training corpus and the word2vec architecture and the training algorithm, the output is one vector per each word. So in the first lesson, I don't know if you were present or not, but there was a question regarding n-grams that was, how do you represent words that have different meanings, such as apple, apple the company, and apple the fruit? Well, with word2vec, we would still obtain one representation, one vector for apple, whether it's the company or the fruit. This work of Mikolov, the first one, presented two neural architectures to learn word embeddings. One was called continuous bag of word, and one called skipgram. And in the second work that he did, he introduced this approach of negative sampling within the self-supervised learning paradigm, which I'll show you later. Continuous bag of word was achieved by a very simple feed-forward neural network that took in input a context. And you can see in here, I don't know if you noticed it before, but we go a bit further away from the idea that the context is the words that precede the word that has to be predicted. So you can see in here, we are at time t. We want to predict the word t, given previous words that we observed at t-1 and t-2, and next words, t+1 and t+2. So word-to-vec, continuous backward word, takes an input. It has this embedding matrix, this lookup table, if you want, like we did for a probabilistic neural language model. These vectors are being compressed together. I'll show you later how. And then the idea is to predict the next word. And the self-supervised learning approach was the following. So imagine that we need to predict heavy. We take an input, the two preceding words, t-1 and t-2 in A, and then the two following words, num and quart. And then the next instance to be fed to the network for training is num, predicting num given this context, a heavy quart saucepan, and so on. We said we have this lookup table that allows us to retrieve the word embeddings. Then, according to the paper, these vectors are being averaged together. It's very simply, because again, the focus is on learning the embeddings, not the prediction in that sense. And then the output is the usual softmax function on which gives an output layer of as many neurons as the vocabulary. Skipgram flips the architecture, essentially. The idea of skipgram is to predict the context given a word. So in this case, the input is heavy, and what the network has to predict is the context. So it should give high probability to words that are corresponding to the preceding and trailing words to the input. There is the negative sampling approach, the improvement that basically allows the network to observe negative examples. So what is being fed to the network is the pivot word, the word that comes in input, quart in this case. There's a mistake, it should be quart and not heavy, but you get the idea. And what is being fed to the network is positive examples, so the context. In this case, will be heavy, num, saucepan, and mix. So that's what we expect the network to predict. So to return the highest probabilities for these words. And then all the other words that are outside the context are negative examples. So what we expect is that the network gives low probabilities to all these words. And of course, it could happen. I think there was an example here. Maybe not, but you can imagine that in the remaining text, there is heavy again. So of course, there will be noise in the data, but this is self-supervised learning. So the good thing is that we just chuck it in. If the corpus is big enough, then eventually the network would learn good embeddings. And of course, you can see there are many more negative examples than the positive examples. So we can decide to sample only 4 negative examples so that we keep the data set balanced in terms of positive and negative examples. Back to the code, we look at two techniques for word embeddings called word-to-vec, the other one is fast text. These are retrieved from this library called GenSim, which is, I think it's still fairly popular, although it runs just on CPU and not GPU. It has word-to-vec implementations and fast text. There's a bunch of hyperparameters that we're not going to delve into it. These word embeddings were already trained, so I'm going to skip this bit. And then we can do the same exercise as we did before for the neural probabilistic language model and see what these models. So I trained continuous backward word model, the skipgram, and skipgram with negative sampling and fast text. I'll tell you something about fast text in a second. So let's focus first on the word-to-vec models. So let's start from continuous backward word, and we want to see the most similar words to onion, and this is what we get. And it was in the hyperparameters, but I trained these models for 5 epochs just to keep it in comparison with the Benjus network. We can look at what skipgram returns as most similar words, similar to continuous backward words, and this is the remarkable bit that when we introduce negative sampling, we get much more, at least expected similar words to onion than what we saw before. Now, there is one thing about word-to-vec, which is very similar to the n-gram approach, which is that the words that are being generated, or that the word embeddings relate to the vocabulary. So for these models, all these word-to-vec models, we have a vocabulary of 5,300 words. So if we want to use a word that is not present in the vocabulary, which is tempe, if you remember last lesson, then we don't have any word embedding. So we are back to the same story that we had last lesson. We have zeros. So how do we return a word embedding for a word that we don't know? This is something that word2vec cannot come up with. Fast text is an alternative approach that essentially breaks down the words into tokens. So there's some approaches that I'm not going to delve into it, that learns how to represent these tokens. And through fast text, then it is possible to retrieve any similar words, even if the word is not in the vocabulary. Now, whether does that make sense or not, that depends on the task, depends on the domain, depends on so many factors. If you look at this, by the way, these are words that are present in the vocabulary, and this very weird word most likely comes from a very quick cleaning that I've done as pre-processing. But if we talk about vector semantics, I don't know how tempera and tempe are similar to each other. Apparently, it's very, very similar, 0.98. And I don't know, tempera, to me at least, because I'm Italian, tempera correlates, it's the same as paint. I'm not really fond of tempe, so to me tempe and paint are somewhat related, but it's debatable, let's say. Or at least temperature, it doesn't really have anything to do with tempe, yet this fast text model returns that word as a very similar word to tempe. There was one thing maybe before getting to the end of this lesson. If you remember what I showed you as a quote from Benjo's paper was that these word embeddings can be initialized. So, well, what happens nowadays is that it is possible to download pre-trained word embeddings and then feed them in whichever network for any downstream task as we want. But this is one question that can be triggered. So imagine we have these word embeddings trained on, I don't know, the whole World Wide Web. And then we want to use them to, I don't know, to generate recipes. And then we get this thing. And we generate a recipe that says, add tempera or add paint to the pot that contains, I don't know, carrots. Are there any consequences to it? And maybe it's something that we can discuss later. To conclude, I think we are slightly above the hour. Sorry about that. We started having a look at how neural networks can be used for language modeling. We looked at the very simplest, the simplest approach, which is feed-forward neural networks. So from an input words to predict the next word. We spent quite some time into this feature vector idea and word embeddings, and then we looked into word2vec and very quickly on the three most important approaches and fast text. This whole lesson was based on this, essentially these three papers that are in the reading material in the repository. These were the chapters that I relied on to make this course. This is a little tutorial on cosine similarity. And if you want to go a bit further on representation learning, you can read this brilliant paper and other ways to represent embeddings, GLOB, as I showed you earlier. And thank you.